Hi everyone, my name is Juan Alvarado. I am a current undergrad at Florida International University and a summer research fellow at the University of Texas at Dallas with the National Science Foundation. The topic of my research and my current research goal is to improve the classification and detection of sarcasm in images by fine-tuning a multimodal visual language model. Please keep note of the word multimodal, you're going to be hearing that a lot. The majority of my research is experimentational in nature, so I have a lot of areas I have to cover during the course of this presentation. My abstract. The primary research goal of my paper in simple terms is this: to get better at classifying sarcasm in images. To do this, I plan to take an open source, pre-trained visual language model, a variation of the multimodal lava model, and fine-tune its weights by a specific method, using a carefully selected dataset that is rich in different types of sarcasm. I will also explain and categorize these various forms of sarcasm and their relevancy to my current research. Here's my introduction. I want to begin by explaining that sarcasm is a complex form of verbal irony, where the intended meaning is the opposite of the literal one or what's inferred. It's not a single concept. There are different and subtle types, which makes it incredibly difficult for AI models to identify correctly. This complexity is at the core of the problem I'm trying to tackle, which is the misclassification of sarcasm in images. My goal, as I've said previously, is to improve how well a pre trained visual language model can identify sarcasm in a one shot scenario. That means when it first sees it. To achieve this, I will be fine tuning this specific model using datasets composed of sarcastic images. My hope is that by this focused training, I will teach the model the complex visual and textual clues needed to improve its overall metrics above the baseline pre-trained model. Why is sarcasm classification important anyway? It's important because correctly identifying sarcasm is a key step towards true complete language comprehension for AI. I believe the secret to doing so lies in the visuals. Misinterpreting sarcasm can cause real world problems, misunderstandings in online communication and customer service. For an AI to perform accurate sentiment analysis, it must be able to grasp sarcasm, whether in text, images, or a combination of both, like a visual language model. I argue that the most crucial clues are visual, like a sarcastic smile, an eye roll, or an image that contradicts the text itself. Because of this, my goal is to specifically teach the model how to connect written text with those subtle visual cues. I'm confident that this method will enable my model to classify sarcasm far more accurately than any bimodal model ever could. Let's explain the linguistic taxonomy of sarcasm, or basically just classify the different types that exist and the ones I hope that by training my model I'll be able to detect. There's propositional sarcasm. This one is the most straightforward type, where the entire proposition of the statement is contrary to the intended meaning. The utterance as a whole is meant to be taken as its exact opposite. Example: what a beautiful day, said during a raging thunderstorm. See the photo below. There's lexical sarcasm. The sarcasm itself is localized to a single word or phrase within the sentence, often an adjective or an adverb. The rest of the sentence may be literal. Example: how thrilling, said by someone watching paint dry on the wall. There's like prefix sarcasm. A statement is prefixed with the word like to explicitly flag it as a denial of the proposition that follows. Example: like that's going to happen. Like when pigs fly. Look at the photo. Finally, there's iaclusionary sarcasm. The sarcasm is not located in the literal meaning of the words, but in the communicative act being performed. The speaker performs a speech act, such as making a promise or offering praise, but with dishonest intent. Example: I love how you always arrive on time, to an employee who is always late. At first, it looks like apparent praise, but in actuality, it's a complaint. Unimodal and multimodal AI models. Let's understand the difference. Before I get into the details of fine tuning, I believe it's important to first distinguish between unimodal and multimodal AI models and explain why I chose one over the other. To illustrate this, I'll use the analogy of our own senses. Just as a person might need to use the full spectrum of their senses to fully grasp a situation, an AI model often requires multiple data streams or modularities to achieve the same. Why a visual language model over just a regular LLM? For my work, I specifically chose a visual language model, VLM, over a simpler model to handle the unique challenges of detecting sarcasm. I found that traditional models, which processes images and text separately and just combine the results, are too limited. They fail to capture the deep and complex interactions between the visual and textual elements. I selected a visual language model because it uses cross-modal attention. This allows the model to create direct links between specific words in a sentence and specific parts of an image. This ability to model the nuanced relationship between what is seen and what is written is absolutely essential for understanding something as complex as sarcasm. Visual language model selection, Tiny Lava, Phi2, SIG, LIP, 3.1 billion parameter. Why Tiny Lava? My model choice comes down to the need to balance high performance and demanding multimodal tasks like fine tuning with the limited resources I have available. This model specializes in creating small yet powerful large multimodal models. The central idea of the Tiny Lava project, which I based my choice on, is that you don't always need a massive model to get great results. Their work shows that by using high quality training data like we are going to do and carefully optimized training methods, smaller models, those under 7 billion parameters, can achieve performance comparable to much larger ones. Let's dive into the Tiny Lava model architecture. The brain, Microsoft Phi, 2.78 billion parameters. I chose Microsoft's Phi 2 to act as my model's language processing brain. Although it's a smaller model, it's powerful because it was trained on curated textbook quality data instead of just random internet content. This gives it surprisingly strong common sense and logical reasoning abilities, which are exactly what I need to interpret the nuances of sarcasm. The eyes, the Google SIG LIP. For my vision system, or the eyes, I'm using Google SIG LLP. This is a significant advancement over older models because it excels at extracting deep semantic meaning from an image, understanding the overall context and message, not just identifying objects themselves. This is far more valuable for my research, as sarcasm often lies in the contrast between an image's meaning and the text. The bridge, the two-layer MLP. Finally, a simple two-layer multi-layer perception or LLP serves as the bridge connecting vision and language. It takes the visual data from the SIG LIP and translates it into a format that the Phi2 brain can understand. This allows both the image and text information to be processed together as a unified whole. This method is known to be both efficient and effective for fusing the two modularities. Training dataset and selection and strategy. For my project, I knew that selecting the right training dataset was the most crucial foundational decision I had to make personally. The future performance of my fine-tuned model is fundamentally determined by the quality and diversity of this data. For a nuanced task like multimodal sarcasm detection, it was essential for me to find a dataset that provides numerous high quality examples covering various types of sarcasm. Most importantly, I needed the data to contain strong, clear signals where the sarcasm arises from the interplay between the text and the visuals themselves. After reviewing the key datasets developed by the research community, I chose the mustard dataset. Mustard, Multimodal Sarcasm Detection Dataset. I selected the mustard dataset because its composition is ideal for my project. The data is sourced from popular TV shows, which provides me with a very clear and well defined example of scripted sarcasm. A major advantage for training my model is that the dataset is perfectly balanced, containing exactly 345 sarcastic and 345 non sarcastic samples. What makes it especially powerful for my work is that it's truly multimodal, providing synchronized text, audio, and video. Most importantly, it includes the conversational context for each sample, which is vital because understanding sarcasm often depends on what is said just before. Finally, the fact that the dataset has been successfully extended by other researchers in the field. For example, with emotional annotations in Mustard++, it gives me confidence in its value and reliability as a solid platform for my experiments. The challenge: adapting the Mustard dataset to work with my model. The main challenge I faced was adapting the video-based Mustard dataset to work with my model, which can only process static images. The core problem: the mustard dataset provides all its text data in a JSON file, but supplies the visual information as raw video clips. The model I'm using, Tiny Lava, is a visual language model designed to analyze static images, not video. This created a fundamental format mismatch that required me to build uh, a custom data pipeline to process a solution. My objective: to solve this, my goal was to create a pre processing pipeline. The main purpose of this pipeline is to go through each video in the dataset and extract one single, highly representative image frame. This frame must effectively capture the visual context at the exact moment the sarcastic or non sarcastic text was spoken. Adapting the mustard dataset to work with my model. Continued. Here I detailed the actual code implementation to create the data processing pipeline for the mustard dataset. For the sake of time, I will proceed to the next slide. If you'd like, you can pause the presentation here to review the code in detail. Ethical considerations to consider prior to fine tuning. Data inherited bias. I acknowledge that my model will inherit a cultural bias because its primary training data comes from American TV shows. This means it will learn a specifically American style of sarcasm and likely won't generalize well to other cultures. It creates a risk that my model could learn and perpetuate stereotypes present in the source material. Subjectivity and ambiguity. I must also be clear that sarcasm is inherently subjective. The correct labels in my dataset are not objective facts, but rather a consensus of human interpretation. Different people can reasonably disagree on what's sarcastic or not, and I recognize this ambiguity as a fundamental limitation of the task itself. Potential for misuse. Finally, I'm aware of the potential for misuse. A model that's good at understanding sarcasm could also be used to generate more effective and nuanced online harassment. Because of this dual use potential, I'm framing my research goals clearly around positive applications, such as creating more empathic conversational AI, improving content moderation by detecting harmful sarcasm in images, or enabling more accurate sentiment analysis. Getting started with fine tuning. Parameter efficient fine tuning, also known as PERF, with QLoRa or quantized low rank adaptation. Why I decided against full fine tuning. I decided against the traditional method of full fine tuning where all of a model's billions of parameters are updated for a new task. I found this approach to be prohibitively expensive and slow for my research. The high computational costs, massive storage requirements for each version, and long training times would have made rapid experimentation impracticable, if not impossible. Parameter efficient fine tuning methods were developed to solve this problem. The core principle of parameter efficient fine tuning is to freeze most of the pre trained model's weights and train only a small number of task specific parameters. This approach dramatically reduces memory usage, cost, and storage requirements, making fine tuning accessible for the scope of this research. QLoRa efficiency to the extreme. To fine-tune my model on a single consumer GPU, I used an advanced technique called quantized low-rank adaptation, which dramatically reduces memory usage. Here's a quick summary of my approach. First, I took the large pre-trained base model and quantized its weights down to a highly efficient 4-bit format. To do this without losing significant performance, I specifically used a 4-bit normal flow, also known as an NF4, a method that is mathematically optimized for neural network weights and preserves more information. To squeeze out even more memory savings, I also applied double quantization, also known as DQ. This technique further compresses the small constants used in the first quantization step, reducing the memory footprint without impacting performance. Finally, to prevent common out of memory errors during training, I relied on page optimizers. This feature acts as a safety net, automatically moving data from the limited GPU memory to the more abundant CPU memory during sudden spikes, which ensures that the training process is stable and it doesn't crash. Training environment setup. I chose to run my research project on Google Colab because it was the ideal environment for my work, offering the perfect combination of accessibility and reproducibility. On the accessibility front, Colab provides free access to powerful hardware, including the NVIDIA T4 GPUs I needed to fine tune my model using QLoRa. This removed the significant barrier of high cost computing and made my research possible. For reproducibility, a Colab notebook functions as a self contained executable document. This encapsulates my entire experiment, from library installations to the training code itself, making it very simple for me to share my research and for others to reliably replicate my findings. Python code implementation in order. To fine tune my model, here's a quick overview of what I did. Imports and initial config. I began by importing all the necessary libraries and functions that my script would need from Torch, Transformers, Perf, and TRL. Step 2, model loading. And what I would consider the most crucial setup, I configured and loaded the base model, specifically using bytes and bytes config to apply the 4-bit QLoRa quantization. Step 3, loading the tokenizer. I loaded the tokenizer from my model and importantly set a padding token. This ensures all text sequences in a training batch are uniform in length. Step 4, data prep and formatting. I then loaded my adapted dataset and used the model's chat template to convert each data point into a properly formatted training prompt. Step 5, perf configuration. Next, I created a LoRa config object to define the LoRa settings, specifying key details like the adapter rank and alpha. And finally, step 6, training arguments and launching the trainer. Finally, I defined all the training hyperparameters, learning rate, batch size, epochs, etc., using training arguments, and then initialize the fine-tuning run with the trainer. Hyperparameters. For my project, I recognize that the hyperparameters are the key settings that control the entire training process. I know that choosing them carefully is crucial for achieving optimal performance, ensuring training stability and avoiding common issues like overfitting. My strategy involves running multiple training cycles where I will modify these settings each time. After every cycle, I will evaluate the model against established metrics. This iterative process will allow me to methodically identify the best combination of settings for my specific task. Here's a reference guide to the key hyperparameters used in this project. You can view it in the table below. Metrics for evaluating fine-tuning success. To objectively measure my model's performance, I'll be using standard evaluation metrics for binary classification. My entire evaluation strategy is based on the four possible outcomes from a confusion matrix: true positive, My model correctly identifies sarcasm when it's positive, true negatives. My model correctly identifies when something is not sarcastic, false positive. My model thinks something is sarcastic when it isn't, a false alarm, false negatives. My model misses the sarcasm entirely. By tracking these four outcomes, I can calculate all the necessary metrics to get a clear and objective picture of how well my model is working. Classification metrics, accuracy. This metric represents the overall proportion of predictions that the model got correct. Since the mustard dataset is perfectly balanced at 50-50, 50% sarcastic, 50% non-sarcastic, accuracy serves as a useful measure of performance. Precision. A high precision score indicates a low false positive rate. This metric is useful in applications where the cost of a false positive is high. Recall. A high recall score indicates a low false negative rate. This metric is critical in applications where the cost of a false negative is high. The F1 score. The F1 score is the mean of precision and recall. It provides a metric that balances the trade off between the two. A model can achieve high precision by being very conservative, but this would lower its recall. Conversely, a model can achieve high recall by being very aggressive, but this would lower its precision. The F1 score is the most important metric for binary classification because it punishes models that are extremely biased towards either precision or recall. Project summary and future work. Here's a quick summary of my progress and future plans. So far, I've successfully built a comprehensive framework for my research on detecting multimodal sarcasm. This includes making strategic decisions on the model, dataset, and the detailed plan I'll use to fine tune a small visual language model for this complex task. Part of my work is still that Part of my future work is that I am still currently in the experimentational phase, actively working to find the best combination of hyperparameters and adjusting explicit prompts for the fine tuning process to achieve the best possible results. I will be continuing this research throughout the upcoming fall semester. Thank you so much for joining me in my presentation today. My name is once again Juan Alvarado. I'm an undergrad at FIU, which is Florida International University, and a National Science Foundation Research Fellow at UT Dallas over the summer. Have a nice day.